So this is work conducted by a few people, Alberto Carrassi, Mark Bouquet, Lambertino, Jim Brechard, and Anna Olsen, also all of the SESI project. So basically the work that we're doing is on melt ponds. So sea ice plays an essential role in the Earth's weather and climate, and there's basically an important feedback loop that you get in sea ice. Effectively, the more melting you have, either through climate change or you can get melting that occurs every summer, the more absorption that you're going to get from the solar radiation. And that will in turn heat up the sea ice and cause more melting. Average globally, the albedo change resulting from the sea ice loss is equivalent to 25% of the direct forcing from CO2 during the past 30 years. So these basically have enormous effect on the climate, not only of the Arctic, but they can then have effects onto the global climate. And each year, about 50%, up to 50% of the sea ice surface is covered in these melt ponds. So we have two examples, photos of melt ponds on the right-hand side. And these melt ponds are poorly understood. They are complex and they are sub-grid scale. So these processes get parametrized. We took a look at, we're wondering basically, the ultimate aim is whether we can use machine learning to improve these parameterizations. So we looked at the Icepack model, which is a state-of-the-art sea ice model, and it's representing many crucial sea ice processes. This is a schematic from Mara Hofstein's thesis, basically showing lots of the processes that the Icepack model has. And we wanted to see how well its melt pond parameterization is performing and how sensitive the whole Icepack model is to changing these parameterizations. So the long story short is that the state-of-the-art sea ice model is highly, highly sensitive to these parameter values in this parameterization, this physical representation of these melt pond processes. So on the left-hand side, you can see there's about 10 years of simulations. So if you start these multiple Icepack models, they will all have exactly the same forcing. The only difference is that you perturb their parameters, the melt pond parameters. And these melt pond parameters are perturbed within known uncertainty ranges. You can end up with a few meters difference in predicted sea ice over only about a decade. So that's basically, you can end up with a difference in predicted sea ice that's about as thick as the sea ice itself, within only 1 decade, as long as you just change parameters within known uncertainty ranges, which is slightly scary. We've done some more sophisticated things, such as like Sobol sensitivity analysis. The long story short is that these parameterizations have varying effects. So there'll be one parameterization as a sort of one-size-fits-all for all locations, but we know that they have differing sensitivity according to the geographical locations as well as the seasonal locations, the season of the year. Effectively, what you have is a complex, poorly understood process. It has a big impact on the climate, and you can start to play around with the parameter values. You get very, very large differences in your model output. So our proposal is constraining and developing these parameterizations is hard, especially with the kind of like physics principles, the bottom-up kind of traditional approaches. So can we use the more modern data-driven approaches where we're basically putting neural networks in to replace these parameterizations? As a first step, we took neural networks. We saw if they could literally learn this parameterization and replace the parameterization in the Icepack model itself. So there are a lot of issues when people have taken neural networks, got them to train them to really, really good, like, R2 scores or whatever, and then they put them in a model and run them online, and the whole thing blows up and it becomes very unstable. So we wanted to see if that would happen just in general, just a sort of proof of concept. And the long story short is, these on the right-hand side are 4 model output of Icepack, and there's the blue lines are, so this is a time series of error over, again, those 10 years. And the blue lines basically are linear regressions where if you can do something that's much more simple, then why bother doing neural networks? But they basically blow the model up. Neural networks can learn and replace a model parameterization. So they seem to be able to learn the melt pond parameterization, and you can actually run it in the Icepack model without destroying it. So now the general thought is, can we improve this parameterization? So I think I've already done the recap, but I'll just say at the end. So they play an important role in climate. There's a substantial sensitivity to their parametrizations, and we can emulate these processes if we have, a perfect model. We feed it perfect information and assume that the Icepack parameterization is perfect. Now we're going, okay, let's use observations and see if we can improve and come up with a better melt point parameterization than the sort of ad hoc approaches that are so currently been developed so far. Long story short is we're able to have an observational-based emulator of Icepack. So the left-hand side are some of the, we take climatological, we take observations. So we've got observations of things like temperature, things such as winds or radiation, and then you also have observations of melt point fraction. And you want to go, okay, so if I've got this amount of, it's this hot or it's this windy, it's this, the amount of radiation's coming down, this amount of precipitation, what are my melt point fraction? So basically we give neural networks a lot of input data over a period of time that we have observations for melt points for. It's like multi-layer perceptrons can actually do this pretty damn well, which is kind of cool. And if we use basically split training and test data in time, so we use about 2018 to 2020 as test data, which represents about 80-20% split. We can get, on the right-hand side, there's a sort of time series of melt point fraction with the observed melt point fraction and neural networks predictions of melt point fraction as well. So effectively, we can get an observational-based emulator of melt point fractions, and we're also trying to improve this with other things, such as the type of ice. So multi-year ice and first-year ice kind of behaves quite differently. So the conclusions, future work, are melt points play an important role in climate. They display substantial sensitivity to their uncertain parameterizations. We can emulate these processes in the model using neural networks without substantial drift or instability. We can take observations, we can learn, neural networks can learn to predict the physics of the melt point state. Now we're looking at basically we've got a neural network emulator, can we put this back in to the Icepack model, to NextSimDG, and so on. So almost all climate models don't actually have a melt point parameterization. HadGem has one, and that's about it. So we're seeing if we can put this emulator back in, observational emulator back in, and then it should, in theory, be used by, or available, hopefully available to world's climate modeling centers. And then other steps are things such as, can we use machine learning for equation discovery of melt ponds so we have something that's physically interpretable? So one of the questions that always comes up with neural networks is, okay, you've trained it, it can predict today's climate, but we can't, the sort of like black box comments. Whereas with equation discovery, you can at least use that to then give something and go, look, we know this conserves energy, we know it conserves momentum and mass, et cetera, et cetera. So those are some of the possible future work that we're considering. So yeah, thank you.